This video is on section 4.3, which is about using functions to count. Okay, so this section is all about counting with functions. And so here on this slide, you'll see three results that involve one-to-one and onto functions. These are going to be used throughout this section in order to count certain objects. If you're having some trouble remembering what a one-to-one function is, what an onto function is, then it might be good to go back and review some of the material from section 2.3. Okay, so our first theorem says that if we have two sets, x and y, and a function from x to y, here x is of size m and y is of size n, if this function is one-to-one, then we know that the size of x must be less than or equal to the size of y. And, you can sort of visualize it in this way. If we're going to have a one-to-one function, then distinct elements in x must be sent to distinct elements in y. And so that means the number of things in y had better be bigger than or equal to the number of things in x, as otherwise it would be impossible for every two distinct things in x to be sent to different things in y. Okay, so the next theorem is about onto functions. So let's suppose, again, we have our same sets x and y, and now our function is onto. Then what that says is that the size of x must be bigger than or equal to the size of y. So here, let's imagine that we've got a nice onto function. So that means that everything in y is used. So since everything in y is traced back to something, something in x, and everything in x is used, that means that the size of x must be bigger than the size of y. So that's this theorem here. And then finally, again, we have our same sets x and y of sizes m and n respectively. If there's a one-to-one correspondence from x to y, then the sizes of x and y must be equal. So that's just a combination of the two theorems, right? Remember, a one-to-one correspondence is a function that is both onto and one-to-one. So that would require m to be bigger than or equal to n. It would also require m to be less than or equal to n. And the only way that can happen is if the two sizes m and n are exactly the same. Okay, here we're going to use the corollary on the previous slide to count games in a single elimination tournament. So here we have a single elimination tournament. Players are paired up in each round, and the winner of each match advances to the next round. If the number of players in a round is odd, one player gets a bye into the next round. The tournament continues until only two players are left. These two players play the championship game to determine the winner of the tournament. So if the tournament has 270 players initially, how many games must be played? So at first glance, this sounds like a really difficult problem. However, we can use that corollary on the first slide to help us solve this problem. So we're going to let G be the number of games played. Okay, that's the thing, that's the set of all games played, and that's the thing that we want to count, all right? However, we can define a function f from the set of games played to the set of players who lose a game, so that'll be L, in the following way. We just let f of x be equal to L, where L is the loser of game x. And this function is both one-to-one and it's onto. Right, because it's onto because for every loser, there must have been a game that they lost, and no two games can have the same loser. So what that means is that if I want to count the number of games in our tournament, that's equivalent to counting the number of losers, right? Remember, the corollary on that first slide said that if I have a one-to-one correspondence between two sets, then those sets are of equal size. So that means that if I want to count capital G, the number of games played, all I have to do is count the number of losers. Well, if there are 270 people in this tournament and only one can win, then the other 269 people must have lost, and hence there are 269 losers, and that means that there are 269 games that are played. Okay, so here's another problem that seems pretty intractable unless we use the corollary on the first slide. So we have these 6 lines that have been thrown down on this page, and what we know about these lines is that every line intersects every other line, and that no 3 lines intersect in a single point. So the question is, in that figure on the previous slide, how many triangles are there? Right, so you could go back to that previous slide and you could try to count all of the triangles that are formed from that collection of lines. So because every line hits every other line, and no 3 lines are intersect in a single point, every triangle then must be formed from 3 lines, right? And any set of 3 lines forms a triangle. So there's a one-to-one correspondence between triangles in the figure and sets of lines, sets of 3 lines. Okay, so all we need to do to count the number of triangles, so counting the number of triangles is equivalent to counting the sets or the collections of 3 lines chosen from 6 lines. And remember, in the last video, we learned how to count the number of, if we have a set of 6 objects, we learned how to count the number of ways to select 3 objects from 6 objects. Right, so here we're selecting 3 lines from a set of 6 lines, so there are 20 ways to do that. Remember, C63 is 6 factorial divided by 3 factorial times 3 factorial. And if you make that calculation, that's 6 times 5 times 4 divided by 3 factorial, which is 6. And that turns out to be 20, just as claimed. So that's a lot easier than just sitting and staring at that figure and trying to identify all of the triangles. So there's a generalization of the notion of one-to-one called n-to-1. So a function from x to y is n-to-1 if every y in the image of the function has exactly n different elements of x that map to it. So let's suppose this is y and this is x, and we have an element here in y. Then the function is, say, 3-to-1. If given an element in y that's used by the function, it's used exactly 3 times back in x. So there are exactly 3 elements of x that are sent to that single y. All right, so again, f is n-to-1 if the set or the collection of x's back in capital X that give rise to y under this function, that the size of that set is equal to n. So n different things in x that give rise to that element of y. Okay, so there's a theorem that corresponds to this. And I think it's probably evident from this figure over here. And that is that if we've got an n-to-1 function from x to y, then x is going to be n times bigger than y. For instance, over here in the example, we would expect x to be 3 times bigger than y. So here we have an n-to-1 function that is on to y. If that happens, then the size of x is n times as big as the size of y. So we're going to use the theorem on the previous slide to count the number of ways that we can rearrange the letters in the word enumerate. Now you might remember from the previous video that we had a similar problem with the word gourmand. Now in that word gourmand, all of the letters were different, and that allowed us to fairly quickly compute the number of rearrangements just using the permutation formula. But here we have a complication in that we have some repeated letters. In particular, these E's are repeated. And so that complicates matters for us. So let's pretend for a moment that we're in a situation like we were with the word gourmand. That is, we're going to take these 3 E's and pretend that they're different for a moment. We're going to call them, E1, E2, and E3. So this will become E1, this will be E2, and this is E3 for the moment. So we're going to imagine that world. And in that world, all of the letters in the word enumerate are distinct. And since there are 9 letters, we can count the number of arrangements of this string just by computing 9 factorial. Right, that's P99. So now let's let y be the number of ways to arrange, or actually let y be the arrangements, the rearrangements of this original word enumerate. So it's y that we want to count. We want to count these arrangements of the word enumerate. So what we're going to do is define a function from x to y. Remember, x is the set of arrangements of this gadget here. So we're going to have a function from x to y defined as follows. So if lambda is one of these arrangements of this doohickey here, then we send it to lambda prime, where lambda prime is the string we get just by removing all the subscripts on the e's. So that's clearly an onto function. And it's going to be turn out to be 6 to 1 because you can always, given one of these strings here, there are 3 factorial or 6 ways to label the e's as E1, E2, E3. So this function that we've just described is onto, and it's 6 to 1. So that means that x is 6 times as big as y, right? But we know that x is 9 factorial. So that means 9 factorial is 6 times as big as y. And so that means that the size of y, that is the size or the number of different ways to scramble the letters in the word enumerate, is 9 factorial divided by 6. So that turns out to be 60,480 arrangements. So here we have another application of this n-to-1 function business as it applies to counting. So we have a group of 10 people sitting in a circle around a campfire. How many different seating arrangements are there? So in this situation, a seating arrangement is determined by who sits next to whom, not by where the ground they sit. So let's agree not to distinguish between clockwise and counterclockwise. All that matters is who your neighbors are, not who is on your left or who is on your right. So clockwise versus counterclockwise doesn't matter, and where you're sitting on the ground doesn't matter. It's just your neighbors that matter. So here we have this useful counting principle called the pigeonhole principle. So what it says is, let's suppose we have a function from set x to set c. And furthermore, let's suppose that the size of x, which is n, is bigger than the size of c, which is r. Then the conclusion is that this function cannot be one-to-one. In other words, there are distinct elements, x and y in capital X, that have the same function values. So we can sort of see this with a picture, right? Let's suppose x has 3 elements and c has fewer elements, let's say 2. Now, what we want to try and do is spread out these function values as much as possible. Okay, so I take here, maybe this first dot goes to that dot in C under my function f, and then maybe this dot goes to that dot in C. Well, now I've used everything in C that I can possibly use, and so something is going to get repeated, right? So that first dot in C is being repeated. And so these elements x and y have the same output. So that will happen whenever x is bigger than c and we have a function from x to c. So here's an example of how one might use the pigeonhole principle. It's a classic example. So let's suppose we have a club with 400 members. Must there be some pair of members who share the same birthday? It doesn't necessarily mean birth year, but same day of the year that they're born. And the pigeonhole principle can help us see that the answer is yes, right? So how do we do that? Well, we let x be the set of all people, so there are 400 of them, and we'll let c be the set of all possible birthdays, so there are usually 365 of them. And we'll define a function f from the set of people to the set of birthdays, where f of x is the birthday of person x. So since the size of x, namely 400, is bigger than the size of c, namely 365, there must be 2 people that have the same birthday. That is, 2 people x and y, where f of x is equal to f of y. So here's another classic pigeonhole principle example. So we have Chandra, who has a drawer full of 12 red and 14 green socks. So in the dark, he goes looking to find a pair of socks that match. And the question is, how many socks must he grab without looking in order to be assured of having a matching pair? So if we let C be the colors of these socks, red and green, there are 2 elements in C. If we let X be the set of socks that Chandra selects, what we need is for, and we define a function from X to C where we if we evaluate f at a sock, we're just checking the color of the sock. Well, what do we need to do? We need to choose x so that the size of x is larger than 2. And then the pigeonhole principle will apply. So we need x to be of size larger than 2, and 3 is the smallest number that's larger than 2. So if he selects 3 socks at random, he's going to have a pair somewhere in there that matches. Okay, here's yet another example of the pigeonhole principle. So we have a round-robin tournament, and that means that every player plays every other player exactly once. So we're to prove that if no player goes undefeated, at the end of the tournament, there must be 2 players with the same number of wins. So here's what we do. We'll let X be the set of players, and we don't know exactly how many players there are, so let's suppose that the size of X, that is the number of players, is equal to N. Okay. Now each player plays everyone else, so that means that each player plays N minus 1 games, because there are N minus 1 other people. And no player wins every game, so the set of possible numbers of wins for any given player is in this set C. It could be 0, it could be 1, it could be anything up to N minus 2. It can't be N minus 1, because if there were N minus 1 wins for a player, then that player would be undefeated. And we're assuming that no player goes undefeated. Okay, so we define our function f from the set of players to the set of wins by declaring f of x to be the number of times player x wins. So notice that the codomain of this function c is smaller than the size of the domain x, and therefore the pigeonhole principle says that there are 2 distinct members of capital X, namely maybe little x and little y, that have the same function value. And that's the same as saying that there exists a pair of players with the same number of wins. Okay, so there's also a generalized notion of the pigeonhole principle. So what it says is, let's suppose we have a set X of size n and a set C of size r. And as in the pigeonhole principle, we have a function from X to C. So what this says is that if n is not only not just bigger than r, but let's suppose it's bigger than some multiple of r. That is, suppose n is bigger than r times some L minus 1. Then there's a subset, U of X, such that U is of size L, and f of X equals f of Y for all X and Y in U. So the regular pigeonhole principle, the one that we've been talking about over the last few slides, so for the regular pigeonhole principle, this L is equal to 2. All right, now there's another way to sort of phrase this theorem, and it's given in this corollary. So again, we have, X being of size n and C being of size r and a function f from X to C. Then again, we're claiming that there's a subset U of X where f of X equals f of Y for any X and Y in U, and that the size of U is this ceiling function of n over r. So this ceiling function, what it does is it just gives you the next largest integer, right? So if you apply the ceiling of 5, well, it's just 5. But the ceiling of 5.1, you go to the next largest integer, which would be 6. Okay, so this corollary is just a rephrasing of the theorem. And so you can pick the one that you feel the most comfortable with. All right, so here's an example using the generalized pigeonhole principle. So we have a website that displays an image each day from a bank of 30 images. In any given 100-day period, show that some image must be displayed 4 times. Okay, so we're going to let X be the set of days, so there are 100 of them, right? And C is the set of images. There are 30 of them. And our function from X to C is going to be the function whose input is a certain day X, and the output is the image that gets displayed on that day. So here, 100, well, that's the size of X. That is bigger than 30 times 4 minus 1. Right? Notice that if you were to take 4 and replace it, if you were to take this and replace it with 5, then the inequality would no longer hold, right? The 30 times 5 minus 1 would not be less than 100. So 4 is the largest number that we can put here. So this is our value of L from the generalized pigeonhole principle. Now 3 would work for L, 2 would work for L, but the idea is to choose L to be as large as possible so that the inequality holds. So L equals 4 is the largest that works. And so what that means is that there's a set of 4 days, there's a set of 4 days in X where the same image is displayed. Okay, here's another generalized pigeonhole principle problem. So we have G being the complete graph on 6 vertices. So remember, what that means is that we have 6 vertices and we draw every single possible edge between vertices. So that gives us the complete graph. So let's suppose that some of these edges are colored red and the rest are colored green. So we have red edges and green edges. Show that there must be some triangular circuit whose edges are the same color. So the first thing we do is we're going to pick a vertex, V, any vertex. So let's suppose this is it right there. That's our vertex, V. And there are 5 edges on V, right? So let's try and draw them in. So there's one. There's one. There's one. There's another one, and there's the 5th one. So those are the 5 edges on V. Now, according to the pigeonhole principle, 3 of these edges must be the same color, say green without generality. Okay, so why is that? Well, we can let X, let's let X be the set of edges, and we'll let C be equal to the set of colors. So remember, there are 2 colors allowable. There's red and green. There are 5 edges. And so we can have a function that goes from X to C that assigns an edge to a color. So the inequality in the generalized pigeonhole principle would give something like this. So 5 is bigger than or equal to 2, which is the size of C, times 3 minus 1, right? That's certainly true. If we take that 3 and replace it with 4, it's no longer true. That inequality does not hold. So what this tells us is that there are 3 edges. 3 edges, that's our value of L in the generalized pigeonhole principle. So there are 3 edges that must have the same color, and we're going to say that they're green. So let's color those in now. So let's suppose, I don't know, let's suppose this edge, and that edge. In fact, it could be all 5 of them that are the same color, but let's just, for the sake of having something to write down here, let's suppose it's these 3 that are colored green. And then the others are the other color, namely red. So let's go ahead and color them red. All right. So now, so we're going to let the other vertices of the edges E1, E2, E3, these are the edges, the green edges, we're going to let them be X, Y, and Z respectively. So let's label them. So let's say this is X, and this is Y, and this is Z. Now X, Y, and Z together form a triangle in this complete graph, right? And if they all have red edges, say, I mean, in other words, let's suppose the situation is this. You know, let's suppose that, you know, we have this situation going on, right? Then we're done, right? Because then we have a triangle, X, Y, Z, where all of the colors are the same. But if all of the colors of the edges joining X, Y, and Z are not the same, then we're still okay. So let's see why that's true. So for instance, let's suppose that one of the edges, say, I don't know, between Y and Z is green. If that's true, then we get a triangle, a green triangle, that incorporates Y and Z and our original vertex V. So either way, we get a triangle where all the edges are the same color. So the last example we did is sort of suggestive of this theorem due to Ramsey, which says that for any positive integers r, k, and l, there's a positive integer n such that if the k element subsets of x, subsets of a set x, with n elements are colored into R colors, then there's a subset U in X, with the size of U being L, whose K element subsets are all the same color. So this thing called a Ramsey number is the smallest n that satisfies the conclusion of the theorem.